In this set of notes, we're going to talk about osmosis. So, our essential question is, how does water moving across cell membranes help maintain homeostasis? Let's begin by looking at some basic information about osmosis and water movement. To start with, we need to know what osmosis is. Osmosis is movement of water across the selectively permeable cell membrane. Remember that cell membranes aren't solid structures. They have tiny pores in them that are made of protein that allow certain substances that are the correct size and the correct polarity to move through that membrane. If the molecules are too large, they're stuck on the side of the membrane that they're on. However, if the molecules can fit through the membrane, then they can move if they're needed inside or if they need to leave the cell. Osmosis is a type of diffusion. Remember that diffusion is passive transport, so no energy is needed. This means that molecules are going to move from an area of high concentration to an area of low concentration. Osmosis does use protein channels, and in the case of osmosis, the protein channel's specific name is an aquaporin. Aqua means water, so you can remember this as water spaces or water tunnels. Let's draw a quick picture of what's happening with osmosis in a cell. I've already drawn this picture for us, so if you need to pause the video to draw it yourself, you can. You'll notice that I've already drawn the semi-permeable membrane. I've put our phospholipid bilayer in, our 2 layers of phospholipids. And then in the middle, I've drawn this big purple blob. That big purple blob is our protein channel. And remember, for osmosis, the specific name is an aquaporin. So that purple thing is our aquaporin. I've also drawn some tiny little blue things that look like Mickey Mouse ears. Those are our water molecules. If we count the water molecules on the top side of the membrane, you'll notice that there are 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm just going to put a little 9 here in parentheses. And on the bottom side of the membrane, there's 1, 2, 3, 4. So we have 4 molecules. That means that on top of the membrane, we have a high concentration. Remember, high concentration means more of something. On the lower part of the membrane, we have fewer molecules, so we have a low concentration. That means less molecules. Now, because osmosis is a type of diffusion, it's going to move molecules from an area of high concentration to an area of low concentration. So I'm going to draw a little arrow to remind myself that that is the movement direction. So you'll notice I have a little water molecule here right in the middle of this aquaporin. And the question is, based on the information I've given you, which direction is this tiny water molecule going? Is it going up, or is this little water molecule going down on our picture? If you said the water molecule is traveling down on the picture, you would be correct because it's moving from an area of high concentration, more water molecules, to an area of low concentration or less water molecules. Something to keep in mind is that water moves in one direction until it reaches something called dynamic equilibrium. As we've talked about before, dynamic equilibrium is where you have an equal amount of water or other substances on both sides of the membrane. Dynamic means that the material in this case water, never stops moving. So after a cell membrane reaches dynamic equilibrium and has the same number of water molecules on both sides, H2O is going to move equally in both directions. So to give you a visual of what that looks like, let me slide my camera down just a little bit. I'm going to draw a box with a semi-permeable membrane, and I'm going to put some water molecules on either side of that membrane. I'll put 3 on this side and 3 on this side. Notice that our number of molecules on each side is exactly the same. 3 on this side, 3 on this side. That means we've reached dynamic equilibrium. So when one water molecule moves to one side, another water molecule moves to the other side. This means that the net movement is 0. What is net movement? Well, net movement is the overall movement. We had one molecule leave the left side. So if we put this in math terms, that would be -1. And we had another molecule join the left side. So that would be +1. -1 plus 1 equals 0. So dynamic equilibrium has molecules moving in both directions when the amount of molecules on both sides of the membrane are even, and the net movement is 0. However, things keep moving. All right, so that's the basics of osmosis. Let's look at some specific prefixes and suffixes that we need to know to be able to determine the direction of water movement in an osmosis problem. All of these prefixes and suffixes have to do with the type of solution that's going to contain a cell. I've listed the prefixes here on the left and the suffixes on the right. So let's get some clear definitions of these prefixes and suffixes. Hyper is going to mean above, or it can also mean more. Hypo with the O means below or less. A word you might have seen that uses hypo is hypodermic. Derma means skin, so hypodermic means below the skin. We use that word to talk about needles that you get shots with. So they are hypodermic needles because the needle goes below your skin to give you the injection. The last prefix on here is iso, and iso means same or equal. A good prefix to use for the solution that we just drew is iso because both sides are equal. Now on the suffix side of the page, we have tonic and osmotic. Tonic refers to the solute. Those are the things that are dissolved. Now, this is not always the rule, but typically in an osmosis problem, the solutes are going to be things like salt, sugar, and starch. The word osmotic just refers to water. Okay, so let's look at some types of solutions using these words. I'm going to keep our handy dandy words right over here to the side as I draw some examples. So here I've got a beaker, and I fill my beaker up with some water. And into that beaker, I drop a cell. The cell has a semi-permeable membrane. And this cell is going to have 15% salt on the outside of the cell. That's a 15. And it's going to have 5% salt inside the cell. Our goal is to determine the direction of water movement. So we want to draw an arrow showing if water will move into the cell, out of the cell, or if this solution is at dynamic equilibrium and it will go both ways. The first thing we need to do is figure out what type of solution this cell is in. So we compare the amounts of solute from the outside and the inside. If we look, 15% is bigger than 5%. So 15% is more. If we go back to our handy dandy prefixes here, the word that we use for more is hyper. So we would label this outside solution as hyper, and we're talking about solute here. So the suffix we use is tonic. So this outside solution is hypertonic. Once we've determined the type of solution, we need to figure out water movement. Now, to figure out water movement, you have to look at where is there more water. To figure out amount of water, we simply take the amount of solute outside the cell, so in this case, 15%, and we subtract that from the total amount of solution around the cell. The total amount of solution is always 100%. 100 minus 15 is 85%. So outside, we have 85% water. We'll repeat the process for inside the cell. We have 5% salt inside the cell. We subtract that from the entire solution inside the cell, which is always 100%, and that gives us 95%. So inside the cell is 95% water. Remember, water moves from high concentration to low concentration. If we compare the two amounts of water, inside and outside the cell, there is more water inside the cell. So our water will move from where there is more water, where I've drawn the dot, to where there is less water, outside the cell. Because water is leaving the cell would shrivel up and shrink. So instead of having this lovely round layer, our cell would start to look something more like a raisin. All right, so let's do another practice problem, because the best way to get good at osmosis problems is just to try them. All right, here's another beaker with another cell inside. We'll make this cell kind of flat. I've put some water in this beaker. And outside the beaker, I will put a 45% sugar solution. And inside the cell, I'll put let me change that, hang on. And inside the cell, I'm going to put an 80% sugar solution. All right, first thing I want you to do is figure out the tonicity of the environment. What does that mean? Well, that means I want to know, is the outside solution surrounding the cell hypotonic, hypertonic, or isotonic? So take a moment, pause the video, and see if you can figure that out. When you're ready, hit play and you can check your answer. All right, let's check our answer. So to figure out tonicity, remember we look at amounts of solute. We want to find if the amount outside of the cell, since we're looking for environment, we want to know is the amount outside the cell more than inside, less than inside, or the same? Well, 45% compared to 80%, 45% is definitely less than 80%. So we use our prefix for less, which is hypo. So this would be a hypo, and we're talking about solute or tonicity, so that would be tonic, hypotonic solution. Okay, so next thing I want you to do is figure out which way will water move. To start with, you need to figure out amounts of water outside and inside the cell. So figure out amounts of water. Pause the video now, try to figure those out, and when you think you've got it, hit play and check your answer. Let's check our answer. Remember, to figure out amounts of water, we subtract the outside amount of solute from 100%. 100 minus 45 is 55. So outside the cell, we have 55% water. We repeat the process for inside the cell. So 100% minus 80 is 20. So inside the cell is 20% water. All right, the last thing I want you to figure out is which way will water move. So I want you to draw an arrow to show water movement. Pause the video now. Try to figure it out. When you think you've got it, play and check your answer. Okay, so to figure out the water movement, remember that water moves from an area of high concentration to an area of low concentration. So we first need to figure out where is there more water. I compare just the two water numbers, 55% to 20% inside. 55 is bigger than 20, so I'm going to put a little dot next to 55 to remind myself that that is more. And I'm going to draw my arrow going into the cell from the bigger number to the smaller number, because water moves from where there's more water to where there's less water. What this will do is this will cause the cell to swell, and it will get bigger and could even burst if it doesn't have a cell wall. So think of it like a balloon. A balloon starts off small, but as you add air to the balloon, it gets bigger. And that's exactly what's happening with our cell here as water is added. All right, let's try one more practice problem and see how you do on it. I'm going to make this one a little bit more challenging for you. I think you're ready. Once again, here's my beaker with a solution in it. And here's a cell. Outside the cell, we have 10% sugar and 30% starch. Inside the cell, we have 60% water. So same questions as last time. I want tonicity of the environment, So the environment of the cell is going to be this solution outside the cell. I want to know amounts of water inside and outside. And I want an arrow to show direction of water movement. All right, so pause the video, see if you can figure it out, and when you're ready, click play and we'll check our answers. Welcome back, guys. All right, so hopefully you were able to at least get through part 1 and part 2. So let's start with tonicity. Now, in this case, things are a little bit weird because I've given you 2 numbers for solutes. Don't let that throw you off. Just add them up, and then you can pretend as if they were the same thing. So 10% plus 30% equals 40%. So we have 40% solute outside. Now we need to know our solute amount inside the cell. Well, if it's 60% water, that means that the whole solution, the solute plus the solvent, equals the solution. So we don't know the solute, that's a question mark, or in algebra, you might call that X. So X plus the solvent, well, that's 60%, equals the whole solution. And the whole solution is always 100%. So now I subtract 60. And since we're doing a little bit of algebra here, X equals 40. So the amount of solute equals 40%. If you needed help getting to that part, pause the video again and now see if you can figure out the tonicity. If you're ready, keep the video playing and let's see what we came up with. So to figure out tonicity, we compare the solute outside to inside. In this case, they're both 40%. So 40% equals 40%, and the prefix we use for equal is iso. And since we're dealing with solutes, we use tonic as our suffix. So this cell is in an isotonic environment. Now for amounts of H2O, remember we go back to that subtraction again. So let me get rid of the problem we just did here. And we'll come back to this equation. All right, so we've already figured out water inside the cell because that was given to us. To figure out water outside, we know that the amount of solute is 40% plus the amount of solvent, that's the water, equals 100%. We subtract 40 from each side, and so our amount of solute is equal, our amount of solvent is equal to 60%. So outside the cell, we have 60% water. So the answer to our amount of water, 60%. All right, last but not least, I asked you to draw an arrow showing direction of water movement. Well, in this case, water inside and outside is equal. So we've reached this dynamic equilibrium. Remember, dynamic equilibrium doesn't mean that water stops moving. It means that water moves at equal rates into and out of the cell. So in this case, because there's not more water in either place, water is going to move into the cell and out of the cell at equal rates. So we draw an arrow that has 2 pointed ends to show water going in and water coming back out. In this case, the cell wouldn't swell or shrink. It would stay the same. All right, thanks for watching this set of notes. If you have any questions or you want to try some more practice problems, then see Miss Morgan or you can watch the video again. Have a great day and thanks for watching.